Hello everyone, I'm Alina and I'm your host today for AT Koeln event. Thank you for joining us and we are so happy to see your responses to our post and Astro Quiz. During Astro Quiz, many of our followers requested to have a talk about pulsars and we have Professor Michael Kramer here with us. So thank you for accepting our invitation, Professor. People who are already worked in pulsar astronomy would be familiar with Professor Kramer. For those who don't know him, I can introduce him. Professor Kramer is the co-author of Handbook of Pulsar Astronomy, or we know as the Bible for Pulsar Astronomy. And he is interested in searching for and exploiting fast rotating neutron stars that are visible as radio pulsars. Specifically, he is interested in the gravitational physics, pulsar and neutron star properties, mysterious fast radio bursts, and binary and stellar evolution. He's also part of the Square Kilometer Array and LOFAR sciences. And he was part of the discovery of two pulsars towards the galactic center. Also, his team discovered the first double pulsar system. Yeah, I know you all are waiting for him to talk. I can hear your mind voice. Without further delay, I'm inviting Professor Kramer to talk. Lean back and enjoy. And the floor is yours, sir.
Thanks for the nice introduction. I have to make sure I'm not... Okay. I'm actually on two laptops here, so I'll make sure I get my presentation right. Yeah, thank you very much for the nice introduction. It's a pleasure to give a talk tonight, and I hope you can see my slides.
Yes.
Excellent. Okay, good.
Excellent.
All right. So yeah, I like to talk a bit about pulsars, which is a type of object that is not only very extreme, but I think everyone who has worked with them also make a lot of fun. And so what I can try to show you tonight is essentially how we study these objects by sitting here on our small planet and trying to understand everything else in the universe, which is quite a bold thing as humans try to do. And one of the things that we try to understand are pulsars, even though after 50 years of discovery, we still don't quite know how they work. But let us go back a few hundred years. This is an image. It should show Tycho Brahe looking at the night sky, where suddenly a new object appeared in the year 1572. That was called a new star. Later was reclassified as what we call a supernova. But clearly something big had happened when they saw this object. These objects are actually quite rare, and typically we see what we call a supernova only once in a century. But it was one about 550 years earlier, 10,054, which was so bright that it was actually observable at daytime for a number of weeks or maybe even months. For some reason, there are no European records of this event to have taken place, but we know from Chinese records that this was indeed an object that appeared in the sky. And I'm sorry, I can't speak Chinese, so I have to take what Wikipedia tells me, but apparently that's the record of the event. So if you look at that same spot today, we can actually see that there is the remnant of an explosion that we call a supernova remnant. And that's how it looks today. You can really see how the star, as I will tell you in the following, has exploded and really spread out into space. And what you see here is indeed the star being destroyed, and that's what we see today. This one, actually, the so-called Krebs supernova, was a different type of what Tycho has observed, but I'll come back to that at the very end of my talk. This remnant is special because it actually has inspired a number of people to think about the origin of the so-called Newton star that I'm talking about in the following. Neutrons were actually only discovered in 1932, and only 2 years later, two astronomers, Bade and Zwicky, they made that very bold statement, which said, with all reserve, we advance the view that a supernova represents the transition of an ordinary star into a neutron star consisting mainly of neutrons. Such a star may possess a very small radius of an extremely high density. So that's a very, very bold, but actually, as you'll see, a very correct prediction. They actually postulated for the first time that supernovae are connected to the birth events of the so-called neutron stars. So let's have a look what actually happens in such an event. First of all, we have what we call a red supergiant. That's a massive star. When it comes to the end of its life, it blows up by producing more and more heat, by producing more and more heavier material in its center, by fusing first hydrogen and then higher elements at the end until iron. It blows up while doing this and becomes a star that is very much bigger than the sun, as you can see here in comparison. We actually have a picture, for instance, of a supergiant. Red supergiant Betelgeuse is a famous supergiant that we may expect to explode anytime soon. And maybe this is one of the supernova in our century. And this is an artistic impression at the bottom here. And this is actually a radio image with ALMA. And this is how we believe a star would apparently look like. So when this star actually still produces energy, that energy can balance the gravity, which would like to make the star collapse. But as long as gravity is, heat is produced and radiation pressure, both can stand gravity. But eventually it runs out of fuel and then gravity wins. And then we have what we call a supernova explosion. This is a nice animation by my colleague Garching, where you can actually see that in this event, when the star explodes, the luminosity exceeds that of an entire galaxy. And hence they are so easy to see from large distances. And for about 100,000 years or so, there's a remnant of the explosion that's visible before it's diffused into the interstellar medium. And this animation here evolves into the Crab Nebula, as you have just seen it in our example. So this is actually a real picture from a telescope on Earth. That's how the nebula looks like, as you've seen before. And if you zoom in into the very center of this, you find a strange star. Actually, I cannot point anyway. The lower right one is actually rather strange star, which didn't seem to have a spectrum like an ordinary star, and so it was a center of speculation for quite some time. And there was another bold prediction, this time by a colleague called Franco, oops, I misspelled his name. So Franco Pacini, a brilliant Italian astronomer who basically predicted in 1967, this star is actually a neutron star and is the remnant of that explosion in line with what Bade and Zwicky had predicted many years earlier. That was 1967. Remember the date because that's kind of important. He made that before actually neutron stars and pulsars were discovered. But let me first explain what a neutron star actually is. As Bade and Zwicky already said, it's actually a star that mostly consists of neutrons. So neutrons are actually kind of special. They're fermions, they are quantum mechanical particles which have a spin of so-called 1/2. That means that they have to follow the so-called Pauli principle, a fundamental law in quantum mechanics, which means you cannot have two quantum particles that are fermions which have exactly all the same quantum numbers, which means in practicalities, you can pack them as dense as you want compared to, for instance, bosons, which you see on the left-hand side, which have a full integer spin. So fermions cannot pack as dense as you like. And we can actually see this also in lab experiments. On the left, you see a boson gas. On the right, you see a fermion gas. And if you try to lower the temperature to some very, very, very small temperatures, this is nanokelvin, You can see that while the boson gas sort of takes a smaller volumes, fermions try to resist and they don't want to become smaller as you lower the temperature. That's because we have this internal Fermi pressure, as we call it. And that's exactly how neutron stars work. As the star collapses, it squeezes the electrons and the protons into neutrons, but then you have this additional Fermi pressure, and that Fermi pressure then resists gravity and prevents that the whole thing collapses further into a black hole. So at the end, we have an object that is quite large. I'll tell you the number in a second. Basically following quantum mechanical laws, preventing it to collapse into a black hole. And that really is a beautiful example how quantum mechanics actually works everywhere in the universe and even in big objects like neutron stars. So how big are they? Oppenheimer and Volkov, the same Oppenheimer who helped building the atomic bomb, and his Russian colleague Volkov, he was actually at Berkeley at the time, they calculated for the first time, what a neutron star structure should look like. And they came up, following this quantum mechanical calculation, that they should have typically a mass of 1.4 times the mass of the sun, but only the size of Cologne, say about 20 kilometers across. So just to put this in comparison, I have a little animation here where you fly towards the sun, we pass it in some close distance, and I put the Earth a little bit closer to the sun than it luckily is. And then we rotate around the Earth for a while, and then I approach a little red dot, which has exactly the size of a neutron star, 20 kilometers across, which you can then compare with the Earth and the sun. And so this object is, 20 kilometers for quantum mechanical scales is huge, but in terms of astronomical scale, in terms of trying to see this with telescopes, it is kind of small. And so the question was, when they did the calculation, would we ever observe these objects? Why should we bother about existence of neutron stars if they're so tiny that we may not be able to see them? Well, just to put it in comparison again, this is how the sky over Cologne would look like if I place a neutron star there. But people in the 1930s only thought in terms of optical astronomy. But it was also just about the time when radio astronomy was born. And so therefore, at the end of the day, radio astronomy delivered the discovery of these neutron stars as observable objects. And so let's say a little bit about radio astronomy. That's the sky as you may see it if you're outside a big city. That's a beautiful image from Axel Mellinger. And you can see clearly a nice band of the Milky Way. You can see the bright spots towards the galactic center, which is hidden by dust clouds. But that's how the sky would look like if you were able to see the lot of streetlights. This is how the sky would look like if you had radio eyes. Again, you see the band of the Milky Way, but you can also see some large-scale structures of some other features that are not of interest for this talk, but that are clearly make the radio sky look somewhat different than the optical sky. But the radio sky is also quite exciting. In fact, it gives you a different view onto the new universe. And as we know nowadays, you call it multi-messenger astronomy. You really need to combine the information of all different types of information, hence in this case electromagnetic spectrum, but also nowadays otherwise, to understand what's going on. So for instance, as an example, look at the galaxies here on the left-hand side. They seem to be kind of unrelated, randomly distributed on the sky. This is an optical image, but if you take a radio telescope and look in the light of neutral hydrogen, which is the sort of most abundant element in the universe, you can see that they're actually giant gas streams of hydrogen going from one galaxy to the other. There's another one which you actually can hardly see in the optical image. And only if you understand that there is this gas, which is only visible in the radio, you can understand the properties of the galaxies. So radio actually gives you a very nice complementary view to the other wavelength. But it can do even more. It is very good in discovering new things and unknown phenomena. And this is our own radio telescope, the 100-meter telescope at Effelsberg, about 50 kilometers south of Bonn, our LOFA station as well. And with that, we look at these radio photons, which are quite low energy compared to other photons, but they're usually the results of very extreme processes, as I will show you in the following. The other advantage of radio photons is that we get lots and lots and lots of them, and we can easily copy and multiply them by electronic means. We can also combine Effelsberg and other telescopes together to form huge synthesized telescopes of the size of the Earth or bigger. And radio waves basically propagate through everything, including dust. And so, for instance, we can look right into the galactic center. And we can also, because we get lots of photons, we can easily measure the polarization. We can really resolve the universe on nanosecond timescales, something that other parts of astronomy struggle with. So, talking about resolving the universe in nanosecond timescales, that's of course a static image. That's one of the major projects done with the Effelsberg telescope. It's the famous Haslam et al. 408 megahertz survey. It's the northern part is done with Effelsberg, and the southern part was done with the Parkes telescope. And so Glenn Haslam, before Effelsberg was complete, he used the Lovell telescope at Jodrell Bank. It wasn't called that at the time, but it was called Mark I. But he used the Lovell telescope to observe the part of the sky before Effelsberg was complete. And Glenn Haslam sadly passed away a couple of years ago, but when you get him drunk, he was able to tell you a story that when he was observing particular part of the sky for the survey, which I marked here on the right-hand side. This is the pen chart recorder of his observation. This is the original picture of the original. And you see this kind of spike emission. This is actually a real emission. And the story goes that Glenn was just about to go to the pub and have a pint of beer when the pen chart recorder was doing something strange thing. It was doing dit and dit and dit. And he thought the equipment was faulty, and he hit it with his hand, and then suddenly the pen chart recorder was quiet again. He obviously fixed it, and he went on to have his pint. What he didn't know was that in this particular moment of time, the telescope actually has slewed over a pulsar, which is actually one of the strongest pulsars in the sky. And that's made the pen chart recording going whoop, whoop, whoop with about a 1 second period. And if he would not have been so eager to go to the pub, but actually maybe follow up what the pen chart recorder was doing, he may have been able to discover pulsars, because as you can see here, this is the 24th of January 1966. So about a year before Pacini made his bold statement about the quark pulsar, and about a year and a half. Well, by the way, this is some Effelsberg data of this pulsar as we observe it today. That's what the pen chart recorder was doing. Now, as I said, 1.5 years later, Jocelyn Bell was doing a PhD in Cambridge. She was building this radio telescope with a supervisor, Anthony Hewish, to observe quasars, which had just been discovered. When she discovered also that the pen chart recorder was doing something strange, and she looked at the output of her recordings, and you can see this on the left-hand side, and there's something called marked pulsar. That's the first signals she saw, basically, in August 1967. She did follow up. She did not want to go to pub and have a pint of beer, but she, in fact, persuaded her supervisor to improve the equipment to get higher time resolution, and they produced the plot that is underneath, the 28th of November 1967. And here you can see clearly that this signal was periodic and regularly spaced in time. And so that was actually the discovery of pulsars. And here again are some pulsars, as you can see them with a modern radio telescope. Okay, so what are they then? There was actually the first idea that this could be indeed the first signal of extraterrestrial intelligence. They call, therefore, in Cambridge, in internal meetings, they also called them LGM1 for Little Green Man 1. But of course, when Jocelyn discovered a few more pulsars in a few weeks later, that kind of explanation seemed to be unlikely. Why would suddenly everyone try to communicate with the Earth? And so therefore they looked as for a more natural explanation. And that natural explanation was actually given by what we now call the pulsar model, where we have a rotating object that is called, in this case, a compact neutron star, which emits a radio beam along its magnetic axis. And as the pulsar rotates, this beam sweeps the sky. Whenever your telescope is pointed towards the pulsar and the beam passes by, you see a pulse as in this animation. So the regularity therefore comes from the rotation of the objects, and one pulse period therefore corresponds to one rotation of this neutron star. So that's how pulsars are now understood, and I'll give you some examples of more of these objects in the following. But there are really extreme objects. They have a very high magnetic field, about 10 to the 12 Gauss. This is 10 to the 12 times larger than the magnetic field, so 1,000 billion times larger than the magnetic field of the Earth. It has a 1,000 billion voltage drop at the magnetic poles that produces extremely hard gamma and X-ray emission. It also produces a large intensive particle stream that you can see here on the right-hand side. These are numerical simulations that calculate that particles constantly emitted by this object. And of course, it's so dense, it's only 20 kilometers across. We have extreme pressures in the interior. The gravitational field is also extremely severe. So if you want to put all these labels on it, it's a quite unpleasant place to be. And landing there is not recommended. However, they are actually, if you stay away from them, quite useful. So just look at the pulse period that we have. The slowest rotating pulse, actually, oops, it's an old slide. It's now 23.5 seconds, so quite slow, only about 3 rotations per minute. And the fastest rotating pulsar has a period of only 1.4 milliseconds. And in between, we have the Graviy pulsar, which I already mentioned. This actually has a period of 33 milliseconds. And we have the famous Wheeler pulsar. This is the strongest in the sky, only visible from the southern hemisphere, where you have a period of 89 milliseconds. I don't know if you can hear this, but this is actually the Wheeler pulsar when you connect a loudspeaker to your radio telescope. If you do this with a Graviy pulsar, it rotates 3 times faster. And if you go to millisecond pulsar, you get this constant tone of a few hundred hertz, in this case 714 hertz. In terms of rotation per minute, this pulsar here shown has a gentle 7 rotation per minute. So I think this is easier to compare. Compare this, for instance, with the fast spinning mode in the laundry washing machine, that can do something like 1,600 rotations per minute. If you look into that, that looks really fast. If you ever earn enough money to own a car like that, that engine may do 20,000 rotations per minute. And if you compare this, however, with a pulsar, in this particular case, it does more than 40,000 rotations per minute. So the physics is extremely severe. And just to give you another feel for this, if you would have a test mass and you let this, oops, this would be 1 meter height, let this drop in 1 meter height, then after already 1 microsecond, it has accelerated to a speed of 8 million kilometers an hour. And that it gives you a feeling for the gravitational field that is happening. The speed of the crater is a significant fraction of the speed of light. You should get rather dizzy. And the gravitational acceleration, in order for this thing not to fly apart, is large. And of course, then if you have this massive thing rotating very fast, what you have is a flywheel. It's a flywheel in space. And that flywheel is so stable in its rotation that these objects really become excellent clocks that we can use for experiments. So I'll give you a flavor of this for the next few minutes, and then we can come what we actually can learn from them further. So what we do is we take a radio telescope like Effelsberg, we observe these objects as they spin, and then we try to simply measure the arrival time of the pulse at the telescope. We call this a TOA, the time of arrival. Usually these pulsars are actually quite weak as radio sources, not as strong as my example that I showed you before. And so we have to fold the data with the right period to increase the signal to noise, and then we measure the time of arrival. That's good. So now we have roughly measured the period. We have an idea about how this pulsar rotates. So we can predict this rotation into the future. We call this a timing model. And then we go back to the telescope after a few weeks, a month, or years, and then we repeat the measurement, and then we can check how good our model is, whether it actually the arrival time that we now measure coincides with the model or not, or whether this is more residual. And if there is a residual, we tweak the model until we know the pulsar with all its parameters. And that method is about 1,000,000 times more precise if we then would just measure pulse periods, for instance, in a kind of Doppler experiment. And that gives you a really nice tool to do precision physics by just counting the rotation of the Newton star. If the pulsar also has a companion, then this time of arrival is modulated by the orbital motion of this pulsar. Let's say the red ball here is a pulsar. It orbits the common center of mass with a blue companion, and sometimes it's further away from us, like here, and then it takes a bit longer for the pulse to arrive. And sometimes it's a bit closer to Earth, like now, then the path is a bit shorter, and the pulse arrives a little early. And so by this variation in arrival time, we can actually measure the orbit to a precision of about 30 meters, regardless how far this pulsar is away. But for the best pulsars, we get a position accuracy in the orbit of about 30 meters. If the pulsar has a companion, it may also actually go affect its life. Maybe some of you know the Hertzsprung-Russell diagram for stars. We have something similar for pulsars. This is what we call a PP dot diagram. It's here on the left-hand side. On the x-axis, we plot the rotational period of the pulsar. And on the y-axis, the spin down, the period derivative. As the pulsar is radiating, it's emitting electromagnetic radiation. This energy that it takes, it is taken from the rotational energy. And so every pulsar slows down by converting rotational energy into electromagnetic energy. And so every pulsar slows down, and so the Crab pulsar is that ball up there at the top left of the diagram becomes slower. Then eventually it dies in this graveyard. But then there's another error part going from the right to the left, out of the graveyard into this lower left diagram of the part of the PP diagram. What happens there is if the pulsar has a companion star, and this companion star may evolve into a giant star by itself, and then it transfer matter in this accretion disk in a kind of an X-ray binary phase onto the Newton star, and by accreting more matter, like a ice skater doing a pirouette, it's also spinning up because it concentrates more matter on the same radius. So that spins up the pulsar from the slow periods where it was at the end to this very fast period that we call a millisecond pulsar. So the accretion of matter adds, of course, mass, but it also increases the spin period, reduces the magnetic field, and at the same time lowers the spin down rate because the magnetic field is lower. And then we can do some precision physics. And I have no inclination to go through these numbers, but this is a kind of a show-off slide because the number in the brackets at the end of these numbers, this is our measurement uncertainty. So for instance, maybe the most precise measured pulse period, at a network in this case, is 2.947108069162 plus minus 3 milliseconds. So the precision is actually 3 attoseconds, 10 to the minus 18 seconds in this case. So that serves you the kind of precision that we can do with our measurements. And again, I won't go into details, but you just see at the type of measurements we can do. We can measure orbital parameters, masses, relativistic effects, even the possible changes in fundamental constants and gravitational wave detection, which I will not have time to talk about. Right. And just one example, this is actually a result of a PhD thesis we did some years ago. We could even use pulsars to measure the mass of Ceres. This is the biggest asteroid in the solar system, by pointing out that in order to understand the pulsar arrival times properly, we need to understand the solar system barycenter, so the center mass of the solar system. And for that, you need to know all the major objects in the solar system, where they are. And if you don't have that knowledge, your data look a bit weird, and you can turn this around and actually measure the mass of these objects in the solar system. And we can do this, for instance, for Ceres to very nice precision. So this is just by looking at the arrival time of pulsars, we can even measure the mass of an asteroid. Now, when I said Newton stars are quantum mechanics in XXL, I kind of suggested these are very simple objects, mostly consisting of newtons. Yes, they're consisting mostly of newtons, but they're anything but simple. They actually are quite complicated. They have a structure, and the structure is you have a solid crust made of iron outside, and if you go further and further towards the center, the density becomes larger and larger, exceeds the nuclear density by about 10 orders of magnitude, and this material then becomes really strange. It becomes super fluid and superconducting at the same time, but in fact it's a liquid. And so we have a solid crust and a liquid interior. This is something we will never be able to produce here on Earth. This is a pressure that our best laboratories will never be able to reproduce. But the important thing is the interior is liquid. How do we know this? Okay, you can do your calculations, but we can actually test this. And if I would be with you physically, I would show you an experiment. So I recorded this morning. You can repeat that later at home, but you need 2 eggs. One boiled, which is solid, and one raw egg, which is liquid inside. And you can do the experiment trying to find out which is the boiled one and which is the liquid one, which is the raw egg. So this is one particular egg. Not very good in rotating it, but if I stop it, it stops. I'll try that. Let me try that again. I stop it and it stops. Okay, so far so good. Let's take another egg. See if that works. So this part where X rotates, I stop it, but it still continues to rotate. Let me try that again. I stop it and it continues to rotate. So obviously the answer is that the solid X immediately stops, while the raw egg, the liquid egg, so to speak, continues to rotate. And the reason is simple, because your finger is only stopping the crust. It does not stop the rotation of the liquid inside in case of the raw egg. And it's exactly how we can figure out that the Newton star is liquid inside, apart from calculating it. For instance, if this Newton star has a star quake, and it happened from time to time in young pulsars, the periods changes suddenly. You can see this here on the right-hand side. This is spin frequency of Wheeler. It's going down as the pulsar slows down. But if you zoom into some of these things, you see suddenly there is a spike in the rotational frequency. This is because there's a star quake. This thing becomes slightly more spherical, and therefore the angular momentum is conserved, and therefore it spins up a bit. But what you can also see is that after this, what we call a glitch, it continues with the same spin down as we have seen before, more or less. And that's because this quake has sort of affected the crust, but it has not affected the liquid interior. And so therefore, the pulsar just continues to rotate as it used to do before. And that's one of the evidences that we know that pulsars are actually liquid inside. Let me skip that. It just shows that it's a very extreme material. So also, of course, I said when you have mass coming from the companion, it increases. And in fact, we we're not only seeing this 1.4 solar mass as quantum mechanics predicts, but as you can see in this diagram on the right, on the left, you can see that some of the pulsars are actually much more massive, up to more than 2 solar mass. So this comes from the accretion of that companion, the dumping matter onto the initial neutron star. But how much mass can you actually put on it? The answer is we don't know. That is described by the so-called equation of states. That's really a particle physics description. So here we enter particle physics, nuclear physics, and they calculate, our nuclear physics colleagues calculate these so-called equation of state. And these equation of state give you a relationship between the mass of an object and the radius, in this case, the Newton star. And as you can see in this diagram here on the top right, all of these equations of state level out at some mass. Any mass larger than that is not possible. But of course, you can also see there's a variety of models, and we don't know what the right model is. So at least with pulsars, we can try to constrain this equation of state to find the right one, for instance, by measuring the masses and see how high we can actually go in this diagram. And you can see we have marked 3 pulsars here. These are 3 pulsars that are about 2 solar mass, and all of these equation of states that level off at a lower mass are already excluded by these pulsar discoveries. So the question is, how do we actually measure these masses, and how can we measure them so precisely, as you can see from the small error bars on the left-hand side? I gave you 2 examples. So the one example is that 2 solar mass, so Newton star that you just saw in this diagram. This was a PhD thesis from a student some years ago. There we observed a pulsar which had a white dwarf companion. We observed the companion with the VLT, and we observed the pulsar with the Effort spectroscope and some others as well. And so from the optical, we basically got the radial velocity of the white dwarf. From the radio, we got the radial velocity, orbital velocities of the pulsar. That gives you the mass ratio. And from the spectrum of the white dwarf, we could actually figure out what the white dwarf mass was, and that allowed us then to infer the mass of the Newton star. And we were very surprised that this was actually a 2 solar mass. That was the highest mass at the time, and got lots of attention for this paper from nuclear physicists who were frustrated that this pulsar was so massive and maybe ruling out the equation of state. There's a much more exciting way of measuring masses. And here I go back to the first pulsar that the companion ever discovered, which was the one by Russell Hulse and Joe Taylor. That's why we call it the Hulse-Taylor pulsar. They used the Arecibo telescope, which you may know from GoldenEye or Contact. It's filled with water in GoldenEye. It's lately got a hole in the surface. It's not that big, but it's out of operation for the moment. Anyway, they used that telescope in 1974 to discover a pulsar which had a period of 59 milliseconds and a companion obviously in an orbit of about 8 hours. And they measured actually the mass of the orbit of the pulsar and the companion using relativistic effects. They could see that for instance, the orbit was shrinking. And the orbit was shrinking at a rate of about 1 centimeter a day. And the reason for that is the emission of gravitational waves. If you have the 2 masses, let me maybe go back on the animation if I can. If you can see on the animation, we have the 2 Newton stars. The companion is also a Newton star, I forgot to say. Then they orbit each other, they produce gravitational waves. So they form the space-time. Those escape in forms of waves, gravitational waves. They again extract energy from the system, and here the system energy is taken from the orbital energy, so the things shrink and eventually will collide in a number of years. The orbital shrinking means that they get closer and closer and closer by 1 centimeter per day, but also means the closest approach we call perastron happens earlier and earlier and earlier and earlier. And that's plotted here on the right-hand side with this diagram called perastron shift. And the blue line would be our expectation if Newton would be correct. And the red line is the prediction of general relativity for gravitational waves. And you can see how beautiful the data points follow the prediction for gravitational waves. And so therefore in 1993, both of them were awarded with the Nobel Prize for Physics. So they not only measured the masses very precisely, but in fact, they got a Nobel Prize on the way, which is not so bad. Some other strange things happening around pulsars are, for instance, planets. The first extrasolar planet was a system outside the solar system was discovered around a pulsar. In this case, a 6 millisecond pulsar, again with Arecibo. This is a work by Alexander Volchan and Dale Frail. And here you can actually see Volchan at the Effelsberg telescope actually on top of the focus cabin, as we also use a telescope to observe this pulsar for a while. And he's also on a stamp in Poland. Some art, as I said, this was the first extrasolar planet ever discovered. Actually, there are 3 planets in that system. And that inspired some artists to think about how such a planet would look like. And you can see here on the right-hand side where the pulsar is. The observer, for instance, on the bottom is on planet C. That's a very inspiring name. Where you can see sort of the 2 other planets and the pulsar in the background. But you have seen how extreme pulsars are and how intense the gamma ray and X-ray and particle emission is. You don't really want to be there, I tell you that. A few years ago, almost 10 by now, that's embarrassing. We discovered a pulsar with the Parkes telescope where the companion turns out to be actually made of carbon, but so dense that it's actually a diamond-like material. And so this pulsar was called the pulsar with a diamond planet around it. And it laid some interesting headlines in the press and suggestions we should hire a spacecraft and fly there to actually mine the planet. Didn't quite work. Our real crown jewel was, actually still is a system that we call the Double Pulsar. Here we have actually 2 pulsars orbiting each other in just 145 minutes. This is an artistic impression. We will zoom into the pulsar system in a second when we pass the Earth. And here there is a relatively fast but old 22 millisecond pulsar orbiting the young, rather slow 2.77 second pulsar. And that happens with orbital velocities of the order of 1 million kilometers an hour. So we have 2 clocks orbiting each other. They're both at very extreme. And so they're actually a very nice and ideal laboratory to test gravity. I'll just give you 2 examples, actually 3 examples for that. For instance, gravity, mistake, I should not, sorry, gravity affects clocks. We know that if there's a special relativistic effect, that if you go fast enough, your clock goes a bit slower. So for instance, at the end of any Formula 1 race, maybe not with Ferrari right now, but certainly with Mercedes, you're fast enough to actually gain some time. When the pilots get out of the car, they're slightly younger than the rest of us, at least in terms of body clocks. Not much, but slightly younger. The effect is a little bit larger if you actually take gravity into account. So for instance, if you put an atomic clock at the bottom of the Eiffel Tower, an identical clock on the top of the Eiffel Tower, after a year, they have a time difference of 1 microsecond. So actually it's not faster, but it's just a longer integration time. So the clock in the gravitational potential goes slower than the clock further away. And that's, for instance, something we have to take into account when we want to use the GPS satellites, which are further away from the Earth potential. But fortunately, the GPS receiver does that already. In fact, the clock on the satellite does it for you. In the pulsar, we have the same thing. So we have 2 pulsar clocks, and sometimes they're further away from each other, then the clock goes faster, and sometimes they're closer together in this case, and then the clock goes slower. And so sometimes this variation in clock speed we can measure with an amplitude of about 383 microseconds per orbit. Pulsars have such a strong gravitational field that they affect space-time in quite a significant way. And in this particular case, when the pulsar A, the fast pulsar, is in the background and it emits a pulse, and it is on superior conjunction, so everything is lined up on the way to Earth, then the pulse has to go through this dip in space-time around the companion. that takes somewhat longer than flat space-time, and we can measure that extra delay, which happens because it's only passing 10,000 kilometers away from the surface. And we can measure this very nicely as an extra delay at the PA conjunction, which you see at 90 degrees along its orbital phase longitude. So this is the extra delay that it needs to take to this curved space-time, and we call this PA delay. Finally, this is my last example to show a GR effect, and I'll come soon to a close. We also see the gravitational waves that we see in the Hounsay-Taylor pulsar in the double pulsar. Here the orbit shrinks with about 7 millimeter a day. So not quite as fast, but we can measure this much more precisely. And the same plot that I showed you before is here with data that are about to be published now. On the left-hand side, you can actually see what happens. So in 85 million years, in this case, the Newton stars collide and produce a black hole and lots of gravitational waves and maybe some other stuff. And that other stuff was actually observed for the first time in August 2017, when we had 2 Newton stars merging. That was observed at high energy, basically with the integral satellite, but also, of course, with gravitational wave detectors. The GRB peak actually peaked slightly later than the gravitational wave burst. So what happened if you looked at the place in the optical? You can see that suddenly a new bright source appeared and eventually disappeared. And that's the remnant of the explosions when these 2 Newton stars collide that produce a gamma ray burst, as we call it these days, and they produce a black hole and some other stuff. And this is a nice animation from ESO. I'll just show it to you again. This is similar to what you've seen before, but I really like this. Here you can see these 2 Newton stars getting closer and closer. Eventually, the gravitational wave emission becomes large enough to be detectable on Earth. That's when the gravitational wave detectors like LIGO pick it up. And eventually, you have this collision and indeed explosion, where again the luminosities so are high that it outshines the entire galaxy, as you could have seen in the previous plot. And all this material but from the Newton stars is basically exploding into space. And that explains actually where our elements in the periodic table come from. So everything, as I told you at the beginning, hydrogen is the most abundant element because that's the natural element of the universe. It's the lightest element. So this and everything in the light blue is coming from the Big Bang, but everything that is in violet is produced by the collision during the collision of Newton stars, including platinum, including gold, including silver. So this is, if you ever wanted to know where the precious metals and expensive metals come from, they come from the explosion and collision of Newton stars. And also the other material that is in your body, for instance, comes from the birth of Newton stars. All the elements like iron and so on, nickel, all what you have in your bloodstreams, that is produced in the birth events of Newton stars. And all the other in white, this is produced in supernova that Tycho Brahe observed when a white dwarf actually explodes and produces supernova. So just to summarize, basically, we are all made of stardust, and all the heavy elements are produced in supernova explosions, and including those that produce Newton stars, and all the stuff that we'd like to wear, some of us anyway, this is produced in colliding Newton stars. So Newton stars are important in quite a different few ways. So let's just come back to this strange star. This is the Graviy pulsar. And indeed, if you look with an optical telescope that has high time resolution, you can actually see that that strange star is indeed a pulsar, just as predicted by Franco Pacini in 1967. This pulsar in the Graviy nebula was actually confirmed in 1968. So it's a bit later after his prediction, but Franco Puccini was absolutely right. A supernova explosion produces a neutron star in a Crab nebula, and at the end also, of course, confirms Barde and Zwicky with their bold prediction from 1934. So all of this sort of fits nicely together in our understanding of neutron stars. So what we have learned: neutron stars and pulsars are really dense. Those neutron stars that have a radio beam pointing in your direction, they're called pulsars, but both of them are neutron stars. Neutron stars, I think, are very extreme. Lots of interesting physics going on there. You can especially use them to test gravity because they're such good clocks. Neutron stars can also have some very strange companions, even planets, but usually white dwarfs and other neutron stars. We're still searching for black hole companions. That's one of the big things that we do in my groups, trying to find a pulsar black hole system. And your body contains material that was created in supernova explosions creating neutron stars. And many of you may be wearing material that was created in collision of neutron stars. So it's highly relevant, as I said. But for me, most importantly, you can also simulate a neutron star at home, take an egg and see what it can do. But for me, most importantly, neutron stars and pulsars are actually a lot of fun. And I really am grateful that I'm allowed to study this in my research. And I hope I could convey some of the fun to you. Anyway, thank you very much.
Thank you so much. It was a very wonderful presentation. And sorry, I cannot like clap now. So on behalf of everyone, and it was really good. So now it's time for us to answer some online questions. Our event is live streamed in YouTube, so we will look forward to their questions. And so there are some questions we already have from audience, like before this presentation, when we announced it. Okay. So we can go through them first. And by that time, whoever is watching in YouTube, they can comment in our live session, live chat. So we will pass these questions. So the first question is, how is angular momentum transferred between a neutron star and its accretion disk?
So eventually the material just falls with its angular momentum into the neutron star. So it's really just the matter falling on. It's like a pirouette when you basically pull your hands together and you concentrate more matter onto the neutron star. Just by putting the mass onto the, well, whenever you have a mass, it has an angular momentum because it comes in a certain impact angle, a certain distance. And if you have friction, that then the material goes closer and closer to the neutron star, eventually concentrate more mass in the same radius, angular momentum has to be conserved, and therefore you transfer angular momentum. And so angular momentum in total has to be conserved. That of the mass that is accreted, that of the neutron star, so together the spin period goes up.
So it can go up and down?
No, it can only go up.
Okay. So the second question was, are there neutron stars whose magnetic axis and rotating axis are the same, or the separation between them is too small? And if so, what will happen?
Yes, we do see such cases. Sometimes the beam is wide enough of the pulsar that you can, or that it's pointing you more or less all of the whole rotation period. So you just see this little movement. It's not perfectly aligned. We don't think we have a 0 degree alignment, but we have a few degrees in some cases. But this is enough to see some variation and to trace out a little bit of the cone. But in fact, the cone is always directed towards the emission cone, and you see emission for a whole rotation period. So we see them. They're not very common, but they are observed.
Okay, your microphone is muted in where your video is visible. So yeah, you can switch off the other one. Yeah.
Yeah, sorry. Mea culpa. Is it better now?
Yes.
Okay. So you didn't hear my answer to the first question then?
No, we could hear it, but we couldn't see your video.
Okay, sorry for that.
Okay. So, and another question was why pulses are so extremely regular? What makes them so regular or precise?
It's because you store so much rotational energy in this rotating body. It's really just a flywheel in space. You know, flywheels basically have a lot of mass. You put a lot of rotational energy in there, and that makes them so stable. If you, for instance, ever try to sit on this experiment in school or university where you get this spinning wheel in your hands, you try to pull it out of the direction of motion of the, it's actually quite difficult because it's the same way why you can ride a bicycle, because you store this angular momentum in the rotating object, and that gives you stability. But it's essentially a very massive flywheel in space, and that's because it's very difficult to disturb the rotation, and that's what makes them so regular. Yes.
Okay, and we're still waiting for some more questions from them.
I could say we know about 3,000 pulsars, for instance,
Mm-hmm.
and we're continuously finding more as we use better telescopes and better techniques. We expect that there are about 20 to 30,000 pulsars in the galaxy that point the beam towards Earth. So there is plenty of new pulsars to be discovered. And usually the more pulsars we discover, the more extreme the higher the probability, of course, that you find some rare systems. And so that's hopefully will then lead to some black hole pulsar system or some other interesting stuff.
So if the pulses are pointing towards us, then only we will be able to see them, right?
Correct.
Yeah, so there may be pulsars which we cannot identify because it's not pointing towards us, or like neutron stars which are like pulsars. But so is there any possibility that we can find them, or yeah.
No, usually they will continue in the spinning in the rotation direction as they do now.
Mm-hmm.
So we will not find them. We can estimate from the pulsars that we observe, from the width of the beam, how many pulsars we are missing. We believe that we are only seeing every 20 to 30% of the pulsars that are existing in the Milky Way and that are active. They also die at some point because the rotation slows down too much that there's no particle produced anymore. But in a few cases, when a pulsar is precessing, for instance, there's a relativistic spin precession and the pulsar spin axis slowly rotates in space, then of course the pulsar comes into view if you're lucky at some point, but it will also disappear at some point. So for instance, the Hals-Taylor pulsar, where we measured this for the first time, the model predicts that it will disappear from our view in 2025. And if you calculate backwards, it has appeared about the time when Hals-Taylor was born. So it's some pulsars come, some pulsars are going, but the majority is stable in their rotation, and those we don't see.
Okay, so okay, there is another question. So can pulsars be used to locate gravitational wave sources?
Yes, they can. Basically, because we can measure the arrival time of pulsars very precisely, the fact that then a gravitational wave passes over the Earth pulsar system changes the distance to a small degree, and that affects the travel time and the detection of the pulsars here on Earth. So by comparing the pulse arrival times in different directions, we can detect the gravitational waves. And although, well, we're trying it, we have experiments running that with that effect. We are missing a sensitivity, maybe about a factor of 2 or 3, but we're working hard to make that sensitivity available to have a detection. And once you have detected gravitational waves, for instance, from a system of supermassive binary black holes in early galaxies, then they merge, they produce gravitation, they produce a binary system of supermassive black holes. They produce gravitational waves, and those we can detect. We can only detect gravitational waves at very low frequencies in nanohertz regime. This is much lower than what LIGO can see, and much lower than what LIGO can see. And eventually, when we also are able to locate the distance of the pulsar very precisely within one wavelength of the gravitational wave, we can triangulate. We can use the pulsar effect on the gravitational wave on the pulsar, we can use the effect on the gravitational wave on the Earth, and that would allow us to triangulate where the gravitational wave comes from. So that, however, needs some higher precision that we don't have yet. So future telescopes like the Square Kilometre Array should be able to do that. But at the moment, we are just working on the detection of gravitational waves as for instance, a whole background of overlapping stochastic gravitational waves. That experiment will, I think, be successful in the near future. But in order to locate them where the gravitational waves come from, that needs some extra sensitivity that we don't quite have yet, but hopefully we'll have also in the future.
Yeah. So we have another question from our viewers. Rishikesh has asked, what generates the emissions? Is the mechanism same for low energy emissions in radio vs high energy, say X-rays?
The short answer is we don't know the exact radio emission mechanism. That is still, after so many years of research, a problem. Basically, it's very complicated. The emission is coherent, so it's like a laser in the radio. It's up to 100% polarized, brightest temperatures of 10 to 30 or more Kelvin. And all these properties are very difficult to easily explain. You have to invoke plasma physics under extreme conditions. You have gravity effects near the surface. So it's a rather complicated physics, and so far we have not succeeded. All we know, we know quite a bit, but we know that the radio emission comes from rather near the surface of the Neutron star, close to the magnetic pole, about a few hundred kilometers above the pole. And you have plasma streaming from the magnetic pole and then eventually radiating in the radio. The high energy emission is coming from outside, further away from the Neutron star towards the edge of the magnetosphere. That is better understood. There are models that can explain the high energy. It's basically you accelerate particles in the outer part of the magnetosphere, and once they're accelerated, they produce gamma ray emission. And that's here we have nice observations of the Fermi satellite over the last 10 years or so that really confirm that model that gamma ray emission is produced in the outer magnetosphere, while we have evidence that the radio emission is produced in the lower part of the magnetosphere. So they are quite different, but the exact details of the radio emission we still haven't solved.
Okay, there are some other questions. How far do the pulsar jets extend?
These are basically, these are electromagnetic beams, right? So the photons continue to go. There is a particle stream that slows down once it has converted its wind basically into electromagnetic radiation. But there are, so I wouldn't call them jets. There are some pulsars where we can observe jet-like features, like an Wheeler pulsar. This is the remnant of the plasma stream, but how we actually detect them, this is electromagnetic radiation that is coming in a cone-like fashion produced by the photons, and they travel on forever. It's just a matter of how bright they are, how far we can detect them. So the furthest pulsars we know so far are located in the Magellanic Clouds. Sorry. Okay. Yeah, Cooper. So the furthest pulsars are away in the Magellanic Clouds, and if you have a bigger telescope, like the FAST telescope in China, we're aiming to look for pulsars in Andromeda. And with the SKA, we can potentially look even a bit further.
And another question is, are there flux loops on the jets?
Again, they are not really
No, not jets. So yeah, but still, question was like that.
Well, there's a plasma wind, and the plasma wind is basically the plasma that is produced near the magnetic poles and streaming outwards. And once they within the magnetosphere, they basically follow the magnetic field lines, because the magnetic field is so strong, 10 to the 12 Gauss or 10 to the 8 Tesla. And so the particles are basically like, the plasma is like pearls on a string. They really follow the field lines. And eventually, when they lost their energy and they're in the outer magnetosphere, when the magnetic field is weaker, they can diffuse. And that's basically what may brighten and provide luminosity for the Crab Nebula, which powers the Crab Nebula. But there is no flux tube as such. What we see is actually a concentrated beam, coherent beam of radio emission.
Another question is about observational limits. Are there observational constraints on the pulsars we can observe in the Milky Way?
Well, first of all, of course, we can only see those that are pointed towards us. We cover that already. Another constraint is simply the brightness of these objects. They are not very bright radio sources. I don't know if you familiar with flux units of radio astronomers. The standard unit is 1 Jansky, which is 10 to the minus 26 watts per square meter per hertz, so quite a small number. So for instance, if you take the radio telescope like Effelsberg and observe all the pulsars for the lifetime of the universe with Effelsberg, then it's just enough energy to light a light bulb for 1 second. So it's not much energy. So they're quite weak. And we're trying to understand, so the furthest we can see, as I said, is to measure clouds. So it's basically the brightness. The other thing that is indeed hampering the detection of faraway pulsars is the interaction with the interstellar medium. The way the interstellar medium is inhomogeneous. It has clumps of electrons. And basically the radio waves are scattered in this clumpy interstellar medium. So they're really sort of distorted in their radiation pattern, and so that diminishes the intensity, because some of the light that should have been received by us is scattered away out of our line of sight somewhere else, and that scattering becomes more severe the further the pulsar is, and so that doesn't help. So that can be beaten by going to higher frequencies, because the scattering goes down with the fourth power of the observing frequency. That, however, has a disadvantage that pulsars become weaker at high radio frequencies. So usually, if you want to find faraway pulsars, you have to find a sweet spot, a big telescope, first of all, to see the weak radiation, and then go to slightly higher frequencies to beat the scattering in the interstellar medium. But so basically, luminosity pointing towards us and scattering are those things that we're usually dealing with if it comes to ability to detect pulsars.
Okay, there is a follow-up question from Rishikesh. If time permits, can you explain how we know gamma radiations are from the outer magnetosphere? If not, would it be possible to share some reading on this?
Sure. Basically, we observe very often a similar beam pulse pattern of the gamma ray emission. It typically has a double cone structure, double peak structure, and we can basically produce maps of how the beam looks for different altitudes. And the best match for what we observe at the gamma ray sort of pulse shape comes from the upper magnetosphere. The other piece of information that we have is the behavior of the spectrum of the gamma ray emission. There is a theoretical work that predicts what, for instance, the spectrum looks like for emission that comes from the lower part of the magnetosphere, that comes from the outer part of the magnetosphere. And if you compare the observed spectra to what has been predicted, then there's a clear winner that it fits better the outer magnetosphere than the inner magnetosphere. And there are some lots of papers. You can go back to Roger Romani or Alice Harding. These are kind of experts in this field. There are some nice reviews by Alice Harding. She works on NASA Goddard, where they compare the expected beam patterns, where they compare the expected spectra that we observe, and the fact that we have observed pulsars, gamma rays, actually even a TeV, so very, very high frequency energies. This is more compatible with the outer magnetosphere than the inner magnetosphere.
Okay, we have another question from Pawan. Is there any model for predicting glitch in pulsars?
No, there isn't. It's the best model we have is kind of a Sandpiler model, where you basically have building up stresses, and eventually something slips away, and then gives rise to glitch. So that's what's called the Sandpiler model, just the frequency of that. There are, however, differences in different pulsars. So some objects, like the crab and the Wheeler, they glitch with a different frequency. One of them glitches very frequently, but has more glitches, and the other pulsar glitches quite a bit more rarely, but has very large glitches. So there's a bimodal distribution among the pulsars. You see some of these pulsars prefer this kind of magnitude and are a bit rarer, and the other one prefers the kind of smaller amplitude, are a bit more frequent. So we don't quite understand where the difference comes from. It has clearly also to do with the fact that the liquid inside it's a quantum liquid. So it has vertices, it's quantized rotation, then these vertices are kind of connected to the crust, and it depends on how connected these superfluid vertices are to the solid crust. And if they get loose, you get this kind of glitch behavior. So they get different kind of models, but we cannot necessarily predict when a glitch happens. It's just, you have just more chance for some pulsars to observe one and less for others. There's one strong correlation I can mention. Young pulsars are those that glitch, and old pulsars glitch very, very rarely. It's not impossible, but the young pulsars, which also they slow down much faster. The slowdown rate is much bigger. So for a crab pulsar, it slows down by about 90 nanoseconds a day. That sounds like a small number. It's actually quite large. It's easily measurable in over a few days of observation, and so there you can think about in a naive model of the star quakes. The pulsar rotates so fast, it's a bit oblate. It's like the Earth, which is not a perfect sphere, but it's oblate, which the Earth is also solid crust and liquid interior, different material though. And once the pulsar slows down, it wants to become a little bit more spherical because the centrifugal forces are reduced. But it cannot adjust so easily because the crust is solid. So eventually there will be tension in the crust building up, and eventually it's released in the star quake. Suddenly it gets more spherical, suddenly it spins up because of angular momentum conservation, and therefore you see this glitch. And so depending on how the stress is built up and the tensions, then you can get glitches. So for the slow pulsars, which will change the spin period very fast, this is more common than for the older pulsars, which don't rotate that fast and don't slow down that rapidly, where they have a much smoother rotation. And in fact, the millisecond pulsars, which are very old and rotate very smoothly, there's essentially no glitch whatsoever.
Okay, I think we are not seeing any more questions, but the live event is like around a minute slow uploaded in YouTube. So we can maybe wait
Sure.
for a couple of seconds, and then after this we have a session which is like we convey the kind of like astro news session. So if you like, you can stay with us and we can discuss some astro news events happened in over the last month, and
Okay.
also about the sky, which is you can observe for the next coming days.
Sounds good. Okay.
Yeah. So I think there are no more questions, and then it was really wonderful time with you, and it was so wonderful talk. And thank you so much from all of us on behalf of AoT Call, and thank you so much.
Thank you very much. It was my pleasure. Thank you. And good luck with the rest of your talk. Thank you.
Thank you.
All right. Good. We can start the discussion session.
Yes, we can.
Yes. So you see the slide?
Yes, you are good to go.
Good. Good to go. Okay. Well, yeah. So we're going to review this past month in astronomy. And yeah, actually some of it was mentioned in this nice talk. So thank you again, Professor Kramer. Yeah, so let's go right to the news that we've had this month. So first, I think this was a couple days after our last event. They finally powered on Ingenuity in flight. This is still in flight. You know that NASA sent Perseverance and Ingenuity to Mars. So Perseverance is the rover that's actually cut off by the slide here, and then Ingenuity is this helicopter that they will power remotely, and they powered it on for the first time. It's due to arrive in Mars in February, I think, next year. But they have to power it on and make sure that everything is working in flight. So it has 6 batteries that they have to keep charged at 35%. They found that keeping a lower charge for the journey is the most beneficial. You would get the optimal battery power at the end. And then when they get to Mars on the full charge with these 6 batteries, they hope to last 30 Martian days, which is 31 Earth days, because Mars rotates slower than Earth. But yeah, so they powered it on, and then they found that everything's working properly. So that's good to hear. Although it's kind of just starting its travel to Mars. So we'll see how this progresses over the months. And then, yeah, this was fairly interesting. They have an image of Mars in ultraviolet light. They call it a night glow. So what happens is that when Mars is facing the sun, or the side that is facing the sun kind of takes all of the carbon dioxide and nitrogen in the air, and it disassociates this and breaks it down to the elements. And then these elements through the atmosphere kind of migrate back over to the night side of Mars. So this dawn-dusk line, as we would call it, the horizon. And then once it gets to the night side and it's not bombarded with all the light from the sun, then it starts to recombine, and then you get, yeah, it just looks like a word in capital letters, but it's nitrogen oxide, NO. And then the formation of this produces the ultraviolet light. So they call this a night glow that they've seen on Mars. And it's just a fairly interesting picture. This, I think, is an artist's representation of it, because you wouldn't get a high resolution image like this.
Yeah, but still it is a very interesting picture.
Yeah, I quite like it. And then, yeah, so what Professor Kramer mentioned, so that this happened this month, which everybody's quite sad about it. Our SIBO was damaged. So what happened was one of the support cables fell down and damaged the surface. Here you can see another image of it. So this hole that you're seeing here looks terrible, but it's only a small portion just by the bowl here. Actually, it's probably on this side, because what happened is that one of these cables that are supporting this walkway snapped and then fell down And these are very, very heavy cables. And they have to be very heavy because that's a lot of weight that they're supporting. But one of these fell down and damaged the surface. So it's not operational at the moment, which is very sad. And this walkway is now crooked and twisted because one of the support cables fell off. So now they can't even do observations. They can't do anything. They have to fix the walkway first and then go to the centerpiece and make sure that that is working correctly before they can take an observation. Luckily, this happened when nobody was taking an observation, so nobody was injured. That is the main good news. Yeah, and so now everybody's going to be rushing to try and make sure that this is working correctly. But it's sad. It's a very old observatory and very important for astronomers. But yeah, they're still investigating the main cause of this. I don't think they've gotten anywhere with it yet. But yeah, we'll see how that progresses. Yeah, so this one might be, if you read a headline like this, it might be a bit concerning. But this isn't a major air leak. I mean, any air leak, I guess, would be major for an International Space Station. But this isn't so bad that it poses a threat to the astronauts on the International Space Station right now. They first observed this leak in September last year, so like a year ago. And then they wanted to, it's gotten progressively worse, and they wanted to kind of vacate the International Space Station, or at least the American side of it, and make sure that, or try to isolate where this leak is coming from. So the astronauts that are on the International Space Station right now, one from NASA and two from Russia, they went to the Russian side of the International Space Station for a weekend, I think. And then NASA engineers could lock some of the modules and try to isolate where the air leak was coming from. But from what I heard, or at least the last news piece I read, they had no luck with that. So they still couldn't find it. But luckily, I mean, a small air leak is not too much of a big deal because they have enough nitrogen tanks, and then they can keep the cabin pressurized. So it's just that they're using up more nitrogen than they would like. But I don't think this is an immediate threat yet. But yeah, we'll see how it goes in the next year.
Yeah.
And this one, yeah, I wanted to talk about this one because this is not word for word from the press release, but this is pretty much the gist of the press release: alien technology in our solar system. So be careful when you're reading a press release. So when astronomers have a result or some paper that they quite like and they think that the public would be interested, they do a press release. And when you do a press release, you have to make it catchy. You have to make it so that the public will read it. And an easy way to do this is to talk about aliens. But this can be a bit concerning. This is not really what the press release or the result was about. They're not researching alien technology in our solar system. They're just thinking of the possible causes of this orbit, or at least the trajectory of this object. So in 2018, they discovered an interstellar object, so not from our own solar system, that came into our solar system. And they called this, it had this long cigar shape from this artist's rendition here. And they called it Oumuamua. I think I'm mispronouncing it, but it's a Hawaiian name. I think it means heavenly body. I forgot. But yeah, so this object is still in our solar system. And what astronomers are observing is that it is actually accelerating, and not accelerating in a way that they would be able to reason. So some people are explaining it by the same effects that cause a comet to change its orbit so rapidly, where the sun heats up some of the ice and converts some of the frozen hydrogen on the surface to convert to hydrogen gas. And then the astronomers are saying that you just can't see this gas right now, and that's what's causing this big object to accelerate. But some other research is being done saying that there's no formation, no way for this to form, and basically, and not have the ice, or it won't have ice on the surface that is hydrogen, and not have ice that would be able to be sublimated and converted into gas so quickly. So this was an offhand remark from the press release that there's some alien technology that's accelerating it, but nowhere in any of the papers published is that an explanation. But this issue is still being debated. I think there's 2 teams of astronomers that are researching this heavily right now. I think this was only a couple of weeks ago, but yeah, there's an old satellite for geophysics, the orbiting geophysics observatory. It was one of 4 observatories that were sent in orbit in 1964, 1965 to research the magnetic environment around Earth. These were retired in the 70s, but they were still orbiting. They were designed like many other orbital satellites around Earth, that they would burn up on re-entry to Earth. So that happened, and that's fine, because you don't want some impact crater from a satellite falling to Earth. So in the news, you might be hearing that they're launching a bunch of Starlink satellites and other satellites, but mainly there's a multitude of Starlink satellites, but all of these are fairly large, but they're designed so that they burn up in the atmosphere if they were to fall back, if they were to retire and then fall back to Earth. So these don't pose a threat to people living on Earth. But yeah, I think this entered the atmosphere just south of Tahiti and then burnt up in the atmosphere over the southern Pacific Ocean. Yeah, and then Kepler is still being analyzed. So the Kepler satellite, which you see here, has spent 9 years in space, or 9 years of dedicated observations. It had its own issues with its K1 and K2 missions, but it has a multitude of data. It had 2 modes. So there was a short cadence mode and a long cadence mode. The short cadence mode was just for 200,000 pre-confirmed satellites or pre-confirmed stars that they would observe every 2 minutes. And then the long cadence mode, which is for the rest of the Kepler fields that you see here, were an observation every 30 minutes. But this retired in 2018, but there's still a large amount of data for us to go to. So it automatically flags potential exoplanet host stars, and then that has to be confirmed by astronomers later. But what a team in Warwick has done is designed the first AI program to automatically confirm these exoplanets. And it has confirmed 50 exoplanets so far. But they're hoping that this will be very useful for, now there's TESS, which is the successor to Kepler. And right now there's a big issue in astronomy that you're having so much more data that's being produced than in previous decades. So there's an issue on how much time do we have to go through all this data. And so AI is one of the solutions that we pick. So yeah, this just kind of proves the success of AI, at least in exoplanet research for all the planet hunters. All right, so in the night sky is a review of what you could see this past month and also what you will be able to see this coming month. This coming month, I couldn't find too many things, so it's mainly going to be about this past month. This is something that I heard about recently, like a few weeks ago. Somebody asked me about this and I had no idea what it was, but apparently this is a hoax that exists. So it started in 2003. In 2003, August 27th, 2003, Mars and Earth were closer than they've ever been for over 57,000 years. This is confirmed through programs, of course. Nobody was recording data 57,000 years ago. But the fallacy was in 2003, there was an email that went around saying that Mars is going to be the same size as the moon in the night sky, which is really false. Mars is twice the size of the moon, I think, about. But it's like, yeah, maybe 200 times as far away as the moon. So even if you had a conjunction event where the moon and Mars could be visible at that time, you would still need, Mars would have to be 71 times as big as the moon, which is not true. So even if you have a conjunction event at this periastron, then Mars will be quite small, and you would still need an amateur telescope to even make out any details of the surface. But this fallacy kind of keeps recurring every 2 years because Mars and the Earth are on a 2-to-1 orbital period relation. So every 2 years, Mars and the Earth kind of get close to each other again at this periastron where their orbits are closed. It's 7 years ago, so I think this was just a throwaway piece for this press article, but it's something to be aware about, that this exists, and don't believe any of the articles telling you that Mars is going to be as big as the moon, because that won't happen. This happened this week, actually. This asteroid came close to Earth. The orbit is still not known because they can't observe it long enough, or they couldn't when they first observed it in 2011. But I think this was just on Monday or Tuesday. This asteroid passed within the lunar orbit, actually, so very close to Earth, and it is about the size of a jumbo jet is the analogy that I read. So it's not that big, but it's not like a meteor or anything. Like in 2013, there was a Chelyabinsk meteor that actually entered the atmosphere above Russia, and it was so large that it created a shock wave in the atmosphere, and it damaged some of the windows beneath. But this is not a meteor. It did not enter the Earth's atmosphere. This just kind of passed through the lunar orbit. This was a near miss. But maybe you would have been able to see it. I couldn't find any images online except for this artist's rendition. But as for this coming month, the main event that I could find is that Neptune is in opposition. So on the 11th of September, it's the best time to get an image of Neptune. So Neptune in opposition would mean that Neptune is on the opposite side of the Earth than the Sun. So its entire disk will be illuminated and you can see it. You would still need a fairly nice telescope to see it because it is not visible with the naked eye. if you're into astrophotography and you have a nice telescope, then you should take a picture of Neptune and send it to us because we'd love to see it. But yeah, that pretty much concludes this session. I will post the references later, but we would like to announce our next event, which will be on October 1st with Professor Frank Verbund. He will talk about astronomy and astrology in history, or kind of how the two are related and how the two differ. And for that, you kind of have to look at how they both started and how they were the same, and then they deviated, one in a scientific direction and one in a different. But yeah, should be a nice presentation. We will post an official announcement, I guess, tomorrow. But yeah, thank you. Happy observing.
Oh, yeah. So thank you for all who all joined us to do online YouTube live events, and we will see you in the next week. So clear skies.
Clear skies. Goodbye.